Chapter 10, Exercise Numericals. Example 10.1. Monochromatic light of wavelength 589 nanometer is incident from air on a water surface. What are the wavelength, frequency, and speed of A. Reflected and B. Refracted light? Refractive index of water is 1.33. Okay. Now see, for reflected light, the medium that remains the same one. When the light ray incident and after reflection, when it propagate, in both the cases, the medium is same one. Therefore, wavelength, frequency, speed, everything that will remain same one. But in refraction, medium changes. Okay. Now lambda given to you, that is 589 nanometer. So 589 into 10 raised to minus 9 meter. And water, that is 1.33. Now frequency, that always remains constant. It is the characteristic of the source. Now refractive index, that is the ratio of the velocity of light in vacuum to the velocity of light in the medium. So refractive index of water, that is C upon V water. So V in water, that is C by N. C, that is 3 into 10 raised to 8 and 1.33. Solve it, you will get the answer. Now wavelength. So velocity, that is lambda into F. So in water we can write VW, that is wavelength in water lambda W into F, and in vacuum C, that is lambda into F. So we can write C upon V water, that is lambda F upon lambda water F. F cancel, so lambda upon lambda water, and as per definition C upon V, that is refractive index. So we can write lambda upon lambda water, that is N water. So lambda water, that is equal to lambda upon N water. Lambda, that is given to you 589 into 10 raised to minus 9 upon N water, that is 1.33. Solve it, you will get the answer. Clear to all of you? Example 10.2. What is the shape of the wavefront in each of the following cases? A. Light diverging from the point source. So point source produces the spherical wavefront. So in first case, the wavefront is a spherical one. B. Light emerging out of a convex lens when a point source is placed at its focus. So when the source is at the focus, it implies that light emerging out of the convex lens will propagate up to infinity. So the propagating waves will be perfectly parallel to each other. So its wavefront will be the plane wavefront. C. The portion of the wavefront of light from a distant star intercepted by the Earth. So point source give you the spherical wavefront. So star will produce the spherical wavefront. But when it reaches at the surface of the Earth, the wavefront is tremendous large one. So for that tremendous large spherical surface, on the surface at any point, if we consider the small portion, then that will be also the plane one. So in C also the answer is plane wavefront. Clear? 10.3. A. The refractive index of glass is 1.5. What is the speed of light in glass? Speed of light in vacuum is 3 into 10 raised to 8 meter per second. B. Is the speed of light in glass independent of color of light? If not, which of the two colors, red and violet, travels slower in a glass prism? Now see, refractive index of glass, that is given to you 1.5. Speed of light in vacuum, that is given to you. Now velocity in glass that we want to calculate. આગળ આવી ગયો આવો example. So velocity in glass, that is C upon refractive index of glass. So 3 into 10 raised to 8 upon 1.5, you will get the answer. Then is the speed of light in glass independent of the color of light? No, it depends on the color of light, because for different colors, the wavelengths are different. Now, which color that is slower in a glass prism, red or violet? So violet color travels slower than the red because the wavelength of violet that is less than that of red. Clear? Example 10.4. In a Young's double slit experiment, the slits are separated by 0.28 millimeter and the screen is placed 1.4 meter away. The distance between the central bright fringe and the fourth bright fringe is measured to be 1.2 centimeter. Determine the wavelength of light used in the experiment. Okay. Now see, here the given information, that is slits are separated by 0.28 millimeter. It implies that small d, that is equal to 0.28 millimeter, that is 0.28 into 10 raised to minus 3 meter. Then capital D, the distance between slit and screen, that is given to you 1.4 meter. Okay. Now the distance between the central bright fringe and the fourth bright fringe. So distance of fourth bright, that is given to you 1.2 centimeter, that is 1.2 into 10 raised to minus 2 meter. And this one is fourth bright. Okay. Now we have the equation for the position of the fringe on the screen, that is n lambda capital D by small d. So for fourth one we can write x4, that is equal to 4 lambda d by d. Therefore lambda, that is equal to x4d upon 4d. This is equal to, now substitute the values, 1.2 into 10 raised to minus 2, small d, that is 0.28 into 10 raised to minus 3, whole thing divided by 4 into 1.4. You will get the answer in meter and then convert it in angstrom. Clear to all of you? Any doubt in this one?
No, sir.
No, sir.
10.5. In Young's double slit experiment using monochromatic light of wavelength lambda, the intensity of light at a point on the screen where path difference is lambda is k units. What is the intensity of light at a point where path difference is lambda by 3? Now see, we have the equation for the intensity at the point of superposition, that is I equal to 4I0 cos square phi by 2. Now here it is given to you when the path difference is lambda, at that time intensity is k unit. So lambda path difference corresponds to 2 pi radian phase difference. So here when the path difference is lambda, we can write phase difference phi, that is 2 pi radian. So now in this equation of the intensity, substitute phi, that is 2 pi. So I, that is equal to 4I0 cos square 2 pi by 2. 2 cancelled, 4I0 cos square pi, this one is 1. So intensity, that is 4I0, but when the path difference is lambda, intensity is k unit, it implies that this intensity, that is k unit, so k, that is 4I0. Now, when the path difference is lambda by 3, then we can say the phase difference phi, that will be 2 pi by 3. Lambda corresponds to phase difference 2 pi. Now substitute this value of phi in this equation. So I, that is equal to 4I0 cos square 2 pi upon 2 into 3. 2 cancelled. So 4I0 cos square pi by 3. Cos square pi by 3, that is 1 by 4. So 4I0 into 1 by 4, but 4I0, that is k. So in terms of k, the intensity, that will be given by k by 4. Clear to all of you? Next, 10.6. A beam of light consisting of two wavelengths 650 nanometer and 520 nanometer is used to obtain interference fringes in a Young's double slit experiment. A. Find the distance of the third bright fringe on the screen from the central maximum for wavelength 650 nanometer. B. What is the least distance from the central maximum where the bright fringes due to both the wavelength coincide? Now see, lambda 1, that is 650 nanometer. So that is 650 into 10 raised to minus 9 meter. Lambda 2, that is 520 nanometer. So that is 520 into 10 raised to minus 9 meter. Now distance of third bright for lambda 1 on the screen. So the equation for the position of the bright fringe on the screen, that we write x equal to n lambda capital D by small d. For third one, we can write x3, that is equal to 3 lambda 1 capital D by small d. Now substitute the values of lambda 1 small d, capital D, small d, that is 2 into 10 raised to minus 3 meter, capital D, that is 1.2 meter. Actually in question, the value of small d and capital D is missing one, that is the printing mistake, but it is there. So now substitute all the values here and then solve. You will get x3 means the distance of third bright for lambda 1 on the screen. Now, suppose on the screen at distance x, n1th bright for lambda 1 and n2 bright for lambda 2 superposed to each other, right? એટલે n1 order ની bright lambda 1 wavelength માટેની અને n2 order ની bright એ lambda 2 wavelength માટેની એક જ જગ્યાએ form થાય છે, means these two superpose. Now when these two superpose, it implies that the distance of both n1 and n2, that is same one. So we can write n1 lambda 1 capital D by D, that is equal to n2 lambda 2 capital D by small d. D cancelled. So n1 lambda 1 equal to n2 lambda 2. So n1 upon n2, that is equal to lambda 2 by lambda 1. So 520 by 650. So the minimum ratio, that is 4 by 5, because here we want the least distance. So we have to consider the least ratio of this one. Means for lambda 1 fourth bright and for lambda 2 fifth bright superpose to each other on the screen. Okay. Now that particular least distance where these two superpose, so we can use either of these two. x equal to n1 lambda 1 capital D by D. N1 that is fourth one, lambda 1 650 into 10 raised to minus 9. Capital D that is 1.2 and small d that is 2 into 10 raised to minus 3. Then solve this one, you will get that least distance where these two superposing. Clear? Next one, 10.7. In a double slit experiment, the angular width of a fringe is found to be 0.2 degree on a screen placed 1 meter away. The wavelength of light used is 600 nanometer. What will be the angular width of the fringe if the entire experimental apparatus is immersed in water? Take refractive index of water to be 4.3. Okay. Now see the position of the fringe on the screen that we give by x or beta, that is lambda d by d. So we can write the angular width that is b by capital D, or sorry, beta by capital D, or directly if we write the equation, the angular width theta that is equal to lambda by d, then also no problem. Okay. Now we know the refractive index, that is the ratio of the wavelength of the light in vacuum to the wavelength of light in that medium. So when the entire apparatus is immersed in the water, we can write the angular width theta dash that is equal to lambda dash by d. Now lambda dash that is lambda upon n water, small d as it is, but this lambda by small d, that is the angular width in air. So we can write the theta dash that is equal to theta upon n water. Theta that is given to you here 0.2 degree. Substitute theta that is 0.2 degree and water 4 by 3. Solve it, you will get the answer. Clear? 10.8. What is the Brewster angle for air to glass transition? Refractive index of glass that is 1.5. So we have the Brewster's law 10 IB that is equal to NG. Okay. At Brewster angle, we get the reflected light that is perfectly plane polarized one. So at that time, 10 of the incident angle that is equal to refractive index of the medium. So we can write IB that is 10 inverse 1.5. Solve it, you will get the Brewster angle, or it is also known as polarizing angle. Now 10.9. Light of wavelength 5000 angstrom falls on a plane reflecting surface. What are the wavelength and frequency of the reflected light? For what angle of incidence is the reflected ray normal to the incident ray? Now lambda that is given to you 5000 angstrom. For reflected light, wavelength will remain the same one, frequency that remains constant. So lambda that is 5000 angstrom, that is 5 into 10 raised to minus 7 meter. Now velocity that is equal to c, because it is reflecting in the same medium air, that is 3 into 10 raised to 8 meter per second. Now c that is lambda into f, we want to calculate the frequency. So frequency that is c by lambda. C that is 3 into 10 raised to 8. Lambda that is 5 into 10 raised to minus 7. Solve this one, you will get the frequency of the light wave. Now, for what angle of incidence it is the reflected ray normal to the incident ray? So when incident ray and reflected ray both are normal, it implies that we can write the angle of incidence plus angle of reflection, that is 90. But we know this thing, angle of incidence that is equal to angle of reflection. That is the law of reflection. So I that is equal to R, therefore we can write 2I that is 90, so I that is 45. Clear? So angle of incidence, that will be 45 degree. Clear? Example 10.10. Estimate the distance for which ray optics is good approximation for an aperture of 4 millimeter and wavelength 400 nanometer. Now the size of aperture A, that is given to you 4 millimeter, so that is 4 into 10 raised to minus 3 meter. Lambda, that is 400 nanometer, that is 400 into 10 raised to minus 9 meter. Now the Fresnel distance for which the ray optics, that is with good approximation, that is ZF equal to A square by lambda. So substitute the value of A, 4 into 10 raised to minus 3, take square of it upon lambda, 400 into 10 raised to minus 9. You will get the distance, that is the Fresnel distance. Clear? Additional exercise, example 10.11. The 6563 angstrom H alpha line emitted by the hydrogen in a star is found to be red shifted by 15 angstrom. So lambda is given to you, delta lambda, that is also given to you. Then estimate the speed with which the star is receding from the earth. So lambda 6563 angstrom, delta lambda 15 angstrom, minus delta lambda by lambda, that is minus V rad by C. V rad, that is delta lambda by lambda into C. Delta lambda, that is 15, lambda, that is 6563, C, that is 3 into 10 raised to 8. Solve this one, you will get the answer. Clear? 10.14. Let us list some of the factors which could possibly influence the speed of wave propagation. 1. Nature of the source. 2. Direction of propagation. 3. Motion of the source and or observer. 4. Wavelength. 5. Intensity of the wave. On which of the factors, if any, does A. the speed of light in vacuum, B. the speed of light in medium, say glass or water, depend? Okay. So speed of light in vacuum, that is constant one, and that is universal constant. So it is independent of any type of factor. Okay. But now if we think about speed of light in the medium, okay, so it does not depends on the nature of the source. Okay, it is not depending on the direction of the propagation. In all the direction in any medium, it will move with the same velocity. Then third one, so motion of source and or observer, it is not depending on it, means independent of it. Then fourth, wavelength, yes, the speed of light in the medium, that depends on the wavelength of it. Then intensity, so it is independent of intensity. Okay. 10.15. For sound waves, the Doppler formula for frequency shift differs slightly between the two situations. 1. Source at rest, observer moving, and source moving, observer at rest. The exact Doppler formula for the case of light wave in vacuum are, however, strictly identical for these situations. Explain why this should be so. Would you expect the formulas to be strictly identical for the two situations in case of light traveling in the medium? So here see, when we think about the sound waves can't propagate without medium. Okay. So 11th standard માં આપણે જોયું હતું કે frequency experienced by listener, right? તો આ બંને કેસની અંદર અલગ-અલગ equations આપણને મળે આ રીતે, right? એટલે આ બંને ફોર્મ્યુલા આ બે કેસમાં ડિફરન્ટ આવે, right? પણ લાઇટના કેસની અંદર in vacuum એ બંને કેસની અંદર ફોર્મ્યુલા સેમ જ રહે છે. Because if we think about the vacuum, then there is no relative motion for medium or observer. Clear? કારણ કે મીડિયમ જ નથી તો પછી રિલેટિવ મોશનનો કોઈ પ્રશ્ન જ નથી. એટલે બંને કેસની અંદર ઇક્વેશન સેમ રહે છે. ક્લિયર? 10.16. In double slit experiment using light of wavelength 600 nanometer, the angular width of the fringe formed on a distant screen is 0.1 degree. What is the spacing between the two slits? Again, simple thing, lambda that is given to you 600 nanometer, that is 6 into 10 raised to minus 7 meter. Theta, that is 0.1 degree, so 0.1 into pi by 180 radian. Now we have the equation for the angular width, that is lambda by d. We want to find this small d, spacing between the slits. So d, that is lambda by theta. Substitute the value of lambda and theta, then solve it, you will get the answer. Clear? 10.17. Answer the following questions. A. In a single slit diffraction experiment, the width of the slit is made double the original width. How does this affect the size and intensity of the central diffraction band? So when you increase the width of the slit, right, then the size of the central maximum that decreases. So if you make the width of the slit double, then the width of the central maximum that reduced to half. B. In what way is diffraction from each slit related to the diffraction pattern in a double slit experiment? So intensity of interference fringes in double slit experiment, that is modulated by diffraction pattern of each slit. આ ટાઈપનો એક એક્ઝામ્પલ પણ આપણે જોયો કે સેન્ટ્રલ મેક્સિમા formed by the diffraction pattern, and in that the interference pattern is accommodated. એટલે જે independent diffraction નું superposition આપણે લઈએ તો interference pattern લઈ લેવાય. C. When a tiny circular obstacle is placed in the path of light from the distant source, a bright spot is seen at the center of the shadow of the obstacle. Explain why. So that is due to diffraction from the edge of the obstacle. It implies that from that opening. So due to the diffraction of the light, okay, central, that will be the bright spot, which one will be surrounded by some faded part. Then D. Two students are separated by a 7-meter partition wall in a room 10 meter high. If both light and sound waves can bend around obstacles, how is it that the students are unable to see each other over even though they can converse easily? Now see here, the diffraction depends on the factor lambda by A. So here for sound waves, lambda is large one. So lambda by A, this factor A, that is the opening of the obstacle, that is large one. Clear? So if this factor lambda by A is large one, diffraction will be more, so one can hear the sound. But if we think about the wavelength of visible range, suppose we take the average, that is 6 into 10 raised to minus 7 meter, then lambda by A, this factor will be very small for the visible light, and therefore one can't see the person standing behind the wall. E. Ray optics is based on the assumption that light travels in a straight line. Diffraction effects disprove this assumption. Yet the ray optics assumption is so commonly used in understanding location and several other properties of images in optical instrument. What is the justification? Again, we can say the diffraction depends on lambda by A. If lambda by A that is very, very, very small, it implies that the diffraction is negligible one. So in that particular case, we can consider the ray optics. Clear?
पोलराइजिंग में हमें पता चला
10.18. Two towers on top of two hills are 40 km apart. The line joining them passes 50 meter above a hill halfway between the towers. What is the longest wavelength of radio waves which can be sent between the towers without appreciable diffraction effect? So it implies that if you don't want the diffraction effect, means we have to consider the validity of ray optics, means we have to find the Fresnel distance here. But the distance that is given to you, 50 meter. Okay. Now, sorry, that is given to you 40 kilometer between these two and hill is midway. It implies that the distance given to you, that is 20 kilometer. So distance of each hill from the hill which is halfway, that is 20 kilometer, 20 into 10 raised to 3 meter. Now ZF, the Fresnel distance, that is a square by lambda, A that is 50 meter. So here lambda, if it is less than A square by Z, then the diffraction effect that will be negligible one. Now substitute the value of A and Z, solve it, you will get the answer. 10.19. A parallel beam of light of wavelength 500 nanometer falls on a narrow slit and the resulting diffraction pattern is observed on a screen 1 meter away. It is observed that the first minimum is at a distance of 2.5 millimeter from the center of the screen. Find the width of the slit. Now lambda, that is 500 nanometer, so that is 5 into 10 raised to minus 7 meter. Then D, the distance between slit and screen, 1 meter. Then position of first minimum, that is 2.5 millimeter from the center. So that is 2.5 into 10 raised to minus 3 meter. So this one is first one. So we can write the position x1, that is lambda capital D upon A. Okay. Now A, that is lambda D upon x1. So you will get width of the slit. Lambda, that is given to you 5 into 10 raised to minus 7, capital D 1 meter, and x1, that is 2.5 into 10 raised to minus 3. Solve this one, you will get the answer. 10.20. Answer the following question. A. When a low-flying aircraft passes overhead, we sometimes notice a slight shaking of the picture on our TV screen. Suggest the possible explanation. So that is due to interference between the direct waves as well as the waves which are received by your antenna, which are reflected from the plane. So direct wave અને જે reflected wave આવે છે, due to superposition of these two, the interference takes place and due to that the picture is shaking one. Then B, as you have learned in the text, the principle of linear superposition of wave displacement is basic to understanding intensity distribution in diffraction and interference pattern. What is the justification of this principle? Because here in superposition principle, we take the resultant displacement, that is the summation of the displacements under the effect of individual waves. So the resultant amplitude of the wave that can be obtained by this superposition principle. And if we have the amplitude of the resultant wave, then we will get intensity, because intensity proportional to square of amplitude. Clear to all of you? 10.21. In deriving the single slit diffraction pattern, it was stated that the intensity is 0 at angles of n lambda by A. Justify this by suitably dividing the slit to bring out the cancellation. Now, if we divide the given slit into n small divisions or small slits, so width of each one, that will be a dash, that is a by n. So now the angle, that is, we can write theta equal to n lambda by a. So here a by n, that is a dash. So we can write the angle theta for one slit, or we can say angular width for tiny one slit, that is lambda by a dash. Now if each smaller slit give you zero intensity, then the combination of all will give you zero intensity. Very simple thing. Clear?